which basically is more applications of differentiation. Does anyone need the solutions? Because I realized that I've forgotten to show the solutions for last discussion, or we are all okay with that before we start?
I'm okay.
Okay, then, so nobody needs it. Okay, perfect. So in this chapter we have, you remember, you can stop me anytime. This is not a monologue. Okay. So in chapter 4, we're going to look at 3 major concepts: graphing, functions. And you can say, again, graphing functions? Yes. A lot of information that we learn from the derivatives, first and second, about the function, and we are going to use that information to graph. It's a major topic. The second major topic is optimization. What is optimization? It's a big branch of mathematics that deals with max-min, maximum and minimum, maximum and minimum for functions, or maxima, minima, plural, for functions. It's a big chunk of mathematics. And the last one is Newton's method. Newton's method of solving equations. For solving equations. There are other tiny topics, 2 small ones, 2 theorems. One is called Rolle, R-O-L-L-E, Rolle's theorem. And the other one is called MVT, mean value theorem. But these are the major topics. With these 2 theorems, we're not going to apply them in any specific problems. We're just going to learn a little bit. We're going to learn what they are and how to apply them in simple applications. Nothing sophisticated here. What is this optimization again? Max-min. It's a big topic, similar to, not the same, but similar to the related rates from chapter 3. So it's a big topic. Not related rates, I'm just saying similar to. I'm just going to erase it from here so you don't get confused. Okay. Before we graph, we're going to look at graphing functions. We have some preliminaries. So we're going to look at the starting point for graphing. And then we're going to talk about these 2 theorems, Rolle's and the mean value theorem. And only then we're going to go in deep, in depth with graphing functions. Okay. So first, 4.1 deals with max-min. Not the max-min and, huge important applications, but just to have an idea about max-min and what they are and how we determine them. And before we look at some graphs, I would like just to mention 2 different things here. We have 2 different types of max-min. Something called local. In some books, you're going to find it as relative. We use these 2 words interchangeably. If we say local max, we mean relative max, or if we say local min, we also mean relative min. Same thing. It doesn't matter whichever you prefer. So local, max, or min. Also, something called global, also called absolute. Absolute. So when we talk about global max, or global min, or absolute max, absolute min, they mean the same thing. Choose the one you prefer, but remember they mean the same thing. And I may use local, you may use relative. We should be able to understand each other. It doesn't matter which one you use. Now, let's talk about what's the difference between the 2. So I'm going to graph a function. Let me use a different color now. So let's say the function starts here and does this. So let's say I have 3 important points here. And I realize that this is the absolute minimum value. So notice that I don't put arrows. In other words, the function does not go everywhere. No, it starts here and it ends here. We're going to look at other functions in a minute, but this is our first example. So this is definitely the absolute minimum. There is no other value that is smaller than this. So b, comma, f of b, so this is our f of x. This point is the absolute minimum. There is nothing smaller than it. It is also the local or relative. How come? What does that mean? So also b f of b is also a relative minimum because the function exists on both sides and all function values are bigger in the vicinity of this x value, not here or here or here, but in the vicinity. The function exists on both sides and all function values are smaller than, are higher than this one is. So this is an absolute minimum because the entire function does not have a lower value of y, but this is also relative minimum because the function values exist on both sides of the point and they are all higher than this height. This point, which is c f of c, is the absolute maximum, but it's not a relative maximum because I cannot show you the open interval. Here I was able to show you the open interval around the point, but here I cannot because the function does not exist on this side. So this one is only an absolute maximum, not minimum, but absolute. I'm going to write in a moment. But it's not a relative or local, whichever you prefer, okay? Because I cannot show you the open interval on both sides. What about this point? This point is not an absolute min. It's not an absolute max, and it cannot be local because the function does not exist on this side. So one thing we're going to write, I'm going to write anyway, is that the endpoints of an interval can never be relative or local. They could be global, but only if it's feasible. This one is the highest y value. So this is the global max. But this one is nothing. It's not the global max. It's not the global min. So I'm going to write, that's my page 2. Can you still, okay. So a comma f of a, nothing. C comma f of c, absolute max. You don't have to write this. Never local at the end point. Never local or relative at the end point. Now, again, before we look at graphs in the book in a moment, I want to graph another function. So this is our f of x. As we see, the function increases till a certain point, then decreases till a certain point, and then increases forever. So this one, this point, I'm going to call it a, of course, f of a. And I'm going to call this b, f of b. Can anyone tell us what is a, f of a, and what is b, f of b?
A is the local maximum and B is the relative minimum?
Yes, the entire point. So a f of a is the local max. and this is the local min. What about absolute? Does this function have an absolute max or absolute min?
No.
No. No absolute max or min in this situation. This is a local max because I was able to show the open interval around the point. I can show the open interval around the point. The other thing I want you to notice, I've been preparing you for this for a long time. So the tangent here has a positive slope. The tangent here has what slope?
0.
Perfect. The tangent here has what slope?
Negative.
Perfect. The tangent here has what slope?
0.
Yes. And the tangent here has what slope?
Positive.
Yes. So notice when we talk about the tangent, and I ask you about the slope of the tangent, you're really giving me f prime of x. That's what you're giving me, and we know that. So I asked you what is the slope of the tangent line here, and you said positive, which means f prime is positive. I asked you what is the slope of the tangent line here, and you said 0, which means f prime is 0. Then I asked you what is the slope of the tangent here, and again, I know I repeat myself as like a broken record. I am a broken record. And then again, 0 here because f prime is 0, and then positive here because f prime is positive. Okay, so now let's look at a couple of problems in the book. I'm just opening, let me share my screen, and we are here. So this is differentiation rules, but it has a lot of applications of differentiation. Now, the correct title here should be more applications of differentiation, because we've been doing a lot of applications. Logarithmic differentiation is an application. Related rates is an application. Differentials and approximations, they're all applications of differentiation. So this title should be more applications of differentiation. It's not important, but I'm just emphasizing that that's what we've been doing for quite a while. Okay, so let's choose a problem. Let's choose a graph and find absolute max, absolute min, and so on and so forth. So let's start with the graph. And then we're going to continue with looking at some information and sketching a graph. Okay, so we can, that is discontinuous, but it has both an absolute maximum and absolute min, and so on and so forth. So right now, I just want us to choose a graph.
Let's do 4.
Okay, let's do 4. Perfect. So can I, if I do this, can I enlarge this for you, or can you see it? Is it possible for me to enlarge this? I don't want to spend too much time. If you have an idea if I can enlarge this. Maybe if I can copy.
If you hold control while you're on the web page and then zoom in with your mouse wheel, I think that might zoom in.
Okay, I'll try that in a second. Let me just see if I can put it in a Word file. If not, I'll try that. So I have this. Okay, much better. Good. Can you all see this? Is it better?
Yes.
Okay, perfect. Good. So let's analyze point A. What would you say about point A?
The absolute minimum.
It is absolute minimum. Perfect. What will you say about this point? We cannot discuss this because it's not a point, but we can discuss this. And before you say anything, remember, as long as I can show the open interval, if I can show the open interval, if the function exists on both sides, which it does, and if I can show that on both sides, the function values are smaller than this value, that will be a local max. It is a little bit confusing because it has a jump, but the function values are smaller than this function value. Here it is. The function value here, I'm going to make up a number because I don't know the scale. I'm going to say it's 10. The ordered pairs on this side, they all have a smaller value than 10. And also on this side. So this is a local maximum. This is not a point. We cannot discuss it. Let's look at this one. As long as I can show that the open interval exists, function values exist, and all of them, left and right, are all smaller than it or larger than it. Well, on this side, the function values are smaller than it, but on this side, the function values are larger than it. So this is nothing. This is a relative max because the function values on the left and on the right are smaller than it, in the vicinity, in the immediate vicinity of it. But here, this side is smaller and this side is larger. Nothing. What about this point? When x equals d.
Relative
Local
minimum.
minimum.
Yes, it is local or relative. Both are correct. Perfect. What about this?
Both relative and absolute.
Absolutely correct. It is the highest y value, so this must be absolute. I can also show the open interval function values on this side and on this side are smaller than it, so it's absolute maximum for this function. We can have 10 absolute maximum as long as they are the same value. But there is nothing else. This is it. It's the highest value. There is no other value like it or equal to it. And it's also local or relative because the function values in the immediate vicinity, the function exists on both sides, and the function values in the immediate vicinity are smaller. What about this one? Can this be, nothing, indeed. Can it be a relative or local?
No.
No, because it's at the end point of the interval, which means I cannot show the function on the right-hand side because it doesn't